All right, so here is a second attempt at this because the first attempt did not show my writing. So I'm just going to test it out, see if that shows. All right, so here is just the meme or whatever, because teachers always talk about sp and d orbitals and then sort of ignore f orbitals. So the f orbital is going to die, and then g orbitals are just hypothetical orbitals. Another meme, chemistry students, physics students, shape of atomic orbitals. So one thing you got to know is S are shaped like a circle, P is shaped like a figure 8, and D is shaped 1, 2, 3, 4. I don't get the bunny and the bucket thing. I don't know why they're scared of a bunny, but and a bucket. So one thing I am going to have you do is circle the valence electrons on your electron configuration. Argon is 1s2, 2s2, 2p6. Argon has 8 valence electrons. The valence electrons are going to be the highest number that I just underlined and the superscript with it. So that is going to be 8 valence electrons. So you know argon has 8 from where it is on the periodic table, but these electrons, this electron configuration also goes through what the electrons are and the shape that they are and so forth. And the highest number is going to be the valence electrons, and that's going to add up to whatever number the valence electrons are based on counting the group number. So the other thing I'm going to do, but it's for extra credit, is to draw how this would look. And this would be an extra credit question. So S is circular, front number is which orbital it's in. That is 1s2. Then we got 2s2, another circular orbital, and then 2p6. Since that front number is a 2, we know that it's in the same orbital. So right here it is 1s, right here it is 2s, and then here we have the p6 there. And so we got 3 p6s because there are 6 total electrons in it. So then the valence electrons are going to be the outermost electrons, and that's essentially going to be electrons on this orbital here. So that makes sense because on that orbital there we have 2 and 6, so 8 total. If you had to write the electron configuration for copper, students are going to most of the time write this top one. But if you Google it or something, you're going to see it often rewritten like this, where essentially the biggest number is written last. So that D goes here. Now, I don't care which way you write it, but if I have these circled valence electrons, it's going to be the amount of electrons that are in the highest principal quantum number, which is the front number. So there's 4 there. So we have 2 valence electrons in copper. Now, the reason why some people rewrite it, or why maybe scientifically it is the right way to write, is because that has 2 valence electrons. So switching around and writing them in order of principal quantum number or front number, or that principal quantum number stands for how far away it is from the nucleus, is a good way to do it. Now, again, I'm not going to have you draw, or I'm going to make it extra credit for drawing the visual and how the electrons move, because we weren't able to get into it, and it's sort of a hard thing to teach, something I haven't taught before, and so I'm learning how to teach it. 1s2, 2s2, 2p6, 2, 4, 6. So 2 electrons in each. Now that front number is on the same thing as the 2p number. 1s2, 2s2, 2p6, 3s2, 3p6. So again, it's going to be figure 8s. 3p6, 4s2. So that's going to be the next. And then it goes 3d9. So those d orbitals are going to be on that third s orbital. It's going to be in the same place as the 3p and the 3s. And that is going to move like a clover. So 1, 2, 3, 4. Now, why isn't it 5? I don't know. So it makes sense to be 5, but based on it being as far away from each other as possible and as close to the nucleus as possible, it's how they, in a geometry 3D sense, move. So bromine here is the top one is how the electron configuration is. What are the valence electrons? Bromine is in group 17. It is a halogen. It's in group 7a. That means it has 5 valence electrons. The front number is the distance away it is from the nucleus. Therefore, those are the valence electrons. Now, I'm going to draw this. It's going to get messy. We'll see how it goes. 1s2, 2s2, 2p6, 2, 4, 6, 3s2, 3p6, 2, 4, 6, 4s2, 3d10, so that's going to go closer, like a clover. 1, 2, 3, 4 on the third. So I know how I'm going to, again, this is extra credit, but I know how I'm going to ask it, and I have an idea. And then anyways, so it's not going to be as messy as this. Then we got a 4p5. And so 1, 2, 3. So that's how you draw it. It looks like a mess. Again, it's extra credit questions. So quantum numbers is, there are 4 quantum numbers for every electron. And essentially it's because no electrons can be in the same place at the same time. But I'm not going to ask it like this. And I'm going to show you how I'm going to ask it in the next. So if I asked you what the quantum numbers are for aluminum. Aluminum, if you look on the periodic table, is 3p1. It ends in 3p1. The 4 quantum numbers for it are 3, the first number. Then the second number, S, is 0, P is 1, D is 2. So the second quantum number is going to be 1 because it's 3p1. The third quantum number, we're going to draw a little box like this. If you look at the periodic table, P is 6 across. We can put 2 electrons in every P. So we're going to go up, and there's just 1 electron. So I'll do another example after this. This might not have been the perfect first example. There's just 1 electron in the P. I'm going to draw the center number, minus 1 plus 1. The third quantum number is going to be -1. The center number is always going to be 0, and then we come backwards and forward. Then since it's pointing up, it's going to be +1/2. So those are those 4 quantum numbers. I'm going to do another example. So here's another example for chlorine. So if we look at the periodic table, chlorine is 3p5. The 4 quantum numbers are going to be the front number, that is the principal quantum number. 3. Then the second number is S is 0, P is 1, D is 2. Since it's a P, it's going to be 1. The third quantum number is we got to draw a box. P, we're always going to draw 3 boxes, and we'll do a D and S after this. We have 5 electrons in it. The superscript is always the amount of electrons. Electrons want to be as far apart from each other, but as close to the nucleus as possible. So that's technically where the nucleus is, if looking at it from, the standpoint that we are with the boxes. P goes up 2, 3, 4, 5. So we only care about the final electron. So we got 0 minus 1 plus 1. That final electron is 0. Or the final electron is in box 0, and then it's pointing down, so it's negative 1/2. That final number is always going to be either positive 1/2 or negative 1/2. If it's pointing up, it's positive. If it's pointing down, it's negative. The first number is just that number. The second number is either 0, 1, or 2, based on if it's S, P, or D. The third number is just the boxes. I mean, look at the pattern of it, and it's not too tough, but it does take some practice. We're going to do a d orbital next. So let's say if I ask what is the quantum numbers for the last electron in palladium. So that's element 46. We look at the periodic table, that's going to end in 3, 4, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 4d8. We have 4 quantum numbers. Front number 4. Second number S, 0, P, 1, D, 2. It's a D for 2. Next number 1, 2, 3, 4. We have 8 electrons. So up, 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 up. 5, 6, 7, 8. So keep in mind, for every d orbital, we draw 5 boxes. For every p orbital, we draw 3. For every s orbital, which we'll do next, is 1 box. So again, every s, 1 box. Every p, 3 boxes. Every d, 5 boxes. And that's because of the amount of electrons across. S is 2, P is 6, D is 10. 2 electrons can go in each box, because electrons, again, want to be as close to the center as possible, but yet as far away from each other as possible. So that's why they fill 1 box at a time and then go to the beginning of the box. So anyways, here, the third quantum number is, I'm going to start in the center, 0 minus 1 minus 2 plus 1. 1, 2, 3, 4, 5. Okay, what did I do wrong here? Oh, I put 0 there, sorry. So 0 is right here. -1, -2, plus 1, plus 2. So that final electron is right here. Therefore, that is a 0. And then it's pointing down, so -1/2. So the 4 quantum numbers for 4d8 for palladium is 420, -1/2. So I'll do an S, a P, and a D orbital real quickly. And then you can practice them. So magnesium, what is the quantum number for magnesium? Magnesium ends in a 1, 2, 3, S2. Therefore, the quantum numbers is 3. S is 0. The next number is up, down, 0, because S's only have 1 box. And then the last number, since it's pointing down, is -1/2. Then let's do a p orbital. So arsenic, element 33, that is 1, 2, 3, 4, 4p, 1, 2, 3, 4p3. quantum numbers, 4, p is a 1. We're drawing 3 boxes for a p orbital. We have 3 electrons, up, 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 0 in the middle, -1 plus 1. So therefore it's plus 1. And then since it's pointing up, it's positive 1/2. So the 4 quantum numbers for arsenic are those 4. Then let's do a D1. We'll do zirconium, element 40. That's going to be 3,4D2. So it's going to be 4, 2 boxes. We draw 5 boxes for D because there's 10 across. You can fit 2 electrons in each box. We're going to start at the leftmost, up, up, then 0 in the middle box of those, because we have to have equal negative and positive charges on both sides. 0 right here, -1, -2, +1, +2. This is the last electron, it's -1. Then it's pointing up, so positive 1/2. So that's essentially it. There's really not, I mean, it's just a matter of following a pattern. Front number, S0, second number is S0, P1, D2. Then you got to draw the boxes. Middle box 0, to the left is negative, to the right is positive. And then up, positive 1/2, down, negative 1/2. So I'll just do one more. Let's see. I don't know what would be the hardest here. I mean, okay, I'll just do one. So I'll do xenon, element 54. It is 2, 3, 4, 5 p6. So we know that the first number is 5, 2, 3, 4, 5. The second number, since S is 0, P is 1, D is 2. Second number is 1. Third number, P, we draw 3 boxes. We have 6 electrons, up, 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 down, down, down. A 0 in the middle, -1, +1. The last electron is the only one we cared about, which is this one right here. +1, since it's pointing down, it's -1/2. So those are the quantum numbers for xenon, 5p6. Here's the ALEX. Why do elements get larger as they move across the periodic table? So why do elements get smaller as they move across the periodic table? So remember, helium is the smallest, or fluorine, and francium is the biggest. So from that, you don't really need to know the trend, because as it gets closer to fluorine, it gets smaller. So across, you know that you're getting smaller, and then up, you know you're getting smaller, because again, fluorine and helium are the smallest. Now we're going to understand why this occurs. Now this occurs because the nuclear charge gets larger. So the center atom, smaller. So as we move across the periodic table, it gets smaller because there are more protons in the center. And that is the nuclear charge. That is the nucleus. And therefore, it gets smaller as we move across. More protons in the middle. So let's say if Taylor Swift cloned herself, the crowd essentially is going to get closer to her because, well, I don't know. You know, it sort of makes sense. But if there's more Taylor Swifts performing, the crowd is going to pack in closer, I guess, is the best thing I got right now. Here is an ALEX example, which is going to have the highest nuclear charge. And so it does say valence electron. So in a sense, you clone Taylor Swift, the people furthest away from Taylor Swift will move closer to her. again, not a horrible analogy, but whatever, or not a good analogy, but we know that as we go across the periodic table, the elements get smaller because there's a higher nuclear charge. There's more protons pulling on the electrons. So all we have to do is find the elements on the periodic table. And we have technetium, which is element 43, ruthenium, which is element 44, cadmium, which is element 48, and zirconium, which is element, so it'd have to be element 40. So the highest nuclear charge is going to be the one to the most right. And so we can look at this, that has 48 protons. So this is going to have the highest nuclear charge. The next one over to the right is ruthenium, then technetium, then zirconium. So the more right it is, the more protons it is. So these are going to all be in the same period, all these questions here. So the more right it is, the more smaller it is because the nuclear charge is larger. So again, helium, fluorine are the smallest. Francium down there on the bottom left is the largest. Now we got more of them. I guarantee you these are in the same period. Again, periods go across the periodic table. And so here we got zinc. Zinc is element 30. Vanadium is element 23. Manganese is element 25. And iron is element 26. So as we go across the periodic table, we know that the radius gets smaller. So first we have vanadium, which has the least strong nuclear charge. So the greatest nuclear charge is going to be the one furthest right, and that is zinc. So I guess that's going to be 1. And then iron 2, manganese 3, vanadium 4. So it's sort of easy because it's essentially whichever ones have the highest amount of valence or the highest amount of electrons. Those are the ones, or protons. Those are the ones that experience the highest nuclear charge, which makes sense. The charge in the nucleus is based on the amount of protons. So now, why do elements get larger as you move down the periodic table? Remember, largest, francium, and smallest, helium or fluorine. And that is because there are more shells. And in the ones further down the periodic table. So here, let's look at oxygen. Oxygen has 8 protons. Total number of electrons is 8. Valence electrons is 6. Number of shells. So if we do 1s2, 2s2, 2p4, we know that it only has 2 shells. 1s2, 2s2, 2p4, because it only counts up to 2. And then we have selenium, which ends with so selenium is element 34. It has 34 protons, 34 electrons. Selenium then has 1, 2, 3, 4, 5, 6. 6 valence electrons. The number of shells, if we look at where selenium is, it's 2, 3, 4, P6. Therefore, we have 4 shells. Then we have sulfur, element 16, total electrons 16, valence electrons 6. Where does sulfur end? It is 2, 3, 4, P4, so it has 4 shells. So yeah, all of them have 6 valence electrons and 4 shells. So this is just meant as a joke. I don't know what this means. Electron spin, explain. So we're talking about -1/2 and +1/2. Hydrogen ball is rotating, except it's not a ball and it's not rotating. Whatever, I have no idea. All right, so this stuff is not on anybody's test here. There's no paramagnetic or diamagnetic on the test for anyone, so I'll just skip those.